Drop an iron nail into a blue solution of copper sulfate, and in seconds you observe an aggressively developing crystalline brown coating on its surface. Take a mound of pure white silver chloride powder, leave it under a harsh light, and watch the structure shift to a dark metallic gray. Chemical equations are often treated like abstract math problems to be balanced for an exam. Viewing them instead as physical ledgers reveals the precise microscopic rearrangement of atoms as they break apart and lock into new structures. We can decode this seemingly chaotic architecture of chemical change by categorizing these atomic rearrangements into 5 primary structural archetypes. Every single one of these structural archetypes is governed by a strict universal constraint: thermodynamic energy flow. A second constraint operates right alongside it: the microscopic transfer of electrons from one atom to another. By understanding these archetypes and the rules that constrain them, chemical reactivity transitions from a list of isolated anomalies into a predictable, rule-bound system of physical mechanics. The first structural archetype is combination. This occurs when multiple distinct reactants merge to yield a single, unified product. If you take solid calcium oxide and react it with water, those independent molecules collide and rearrange their bonds to form a single structure, calcium hydroxide. The second archetype is the exact structural inverse, decomposition. Here, a single compound breaks down into simpler, separate substances. Because existing chemical bonds are stable, breaking them apart requires an external input of energy, typically heat, light, or electricity, to force the atoms apart. When that white silver chloride powder turns gray, it is because incoming light energy strikes the lattice, fracturing it into separate silver and chlorine components. This mandatory exchange of energy, whether it is absorbed to break bonds or released when new bonds form, allows us to categorize all reactions thermodynamically. This table compares exothermic and endothermic reactions. In the left exothermic column, combination reactions, like calcium oxide and water, release energy, making surroundings warmer. In the right endothermic column, decomposition reactions, like calcium carbonate, absorb energy, cooling their surroundings. In the architecture of chemical change, energy is never an incidental detail. It must be rigorously accounted for as either a fundamental reactant or a guaranteed product. Beyond molecules merging or splitting, elements frequently compete against each other for chemical bonds. This brings us to the third archetype, displacement. This occurs when a highly reactive element aggressively evicts a less reactive element from an existing compound. When that iron meal was submerged in the copper sulfate solution, the iron physically displaced the copper from the sulfate group, simply because iron sits higher on the reactivity hierarchy. The iron successfully takes the sulfate partner, leaving the copper isolated as a solid coating. The fourth archetype is double displacement. This involves a mutual bilateral exchange of ions between two entirely different compounds. Effectively, the two original compounds simultaneously swap their partners. A highly visible subtype is precipitation, where the newly swapped partners form an insoluble solid. If you mix soluble lead nitrate with soluble potassium iodide, the free-floating ions swap instantly. The lead and iodide ions lock together into a dense solid cluster. That resulting lead adidide is a distinct yellow precipitate falling out of the aqueous solution. These displacement archetypes prove that atomic swaps are not random. Their outcomes are strictly dictated by inherent elemental reactivity and rigid rules of solubility. There is a final concept connecting all of these processes: oxidation-reduction, commonly referred to as redox. Redox functions as the mechanical engine of electron exchange, operating simultaneously during these structural changes. The classical diagnostic model to track this defines oxidation as the addition of oxygen or the removal of hydrogen. Reduction is the exact inverse. We can test this diagnostic model on a multi-substance reaction, like manganese dioxide reacting with hydrochloric acid. Let's isolate the hydrochloric acid on the reactant side. Notice that it loses its hydrogen to become chlorine gas. Following our model, this loss of hydrogen identifies the hydrochloric acid as the substance being oxidized. Now isolate the manganese dioxide. It loses its oxygen to become manganese chloride. That loss of oxygen identifies the manganese dioxide as the substance getting reduced. The substance that forces the oxidation by giving up its oxygen, the manganese dioxide, is defined as the oxidizing agent. The substance that executes the reduction by taking that oxygen away, the hydrochloric acid, is the reducing agent. By tracking the gain and loss of oxygen and hydrogen, we create a visible map of the otherwise invisible shift in charge between these reactants, the underlying flow of electrons that powers the reaction. We now have a complete toolkit for reading the physical ledger of chemical reactivity. We start with the 4 structural archetypes: combination, decomposition, displacement, and double displacement. Categorizing reactions into these 4 bins allows us to accurately predict the structural outcomes of complex atomic collisions. To understand exactly why those collisions result in a specific outcome, we apply our 2 universal constraints. We apply the thermodynamic lens to track exothermic and endothermic energy transfer. And we apply the redox lens to map the exact flow of electrons. Through this framework, chemical reactivity emerges as a predictable, elegant system of physical mechanics.